Okay, so welcome to our Friday's webinar, seminar webinar. Good afternoon. We have Dr. Garry Kemp from the University of Johannesburg. He's been visiting us here the whole week, and today he's ready to give us a nice talk on his recent work. Yeah, Garry, please. I think in the audience are only fans. Don't need to introduce it too lengthy. So you're most welcome to start.
No, great. Thank you, Francesco. Thank you so much for hosting me and having me around this week and meeting everyone. It's really been fantastic. So yeah, I hope to tell you today about some recent work that I've done. And it's based on this archive number. So that can highlight, so that's good. So, okay, let's maybe I try and go full screen first of all. Full screen. Great. So, okay, so there is some motivation for the work that I'm going to try and talk about coming from high energy physics and this ADS-CFT story. So firstly, the half BPS sector of what's called N=4 super Yang-Mills theory with the UN gauge group. Now, the details of that is not super important at all. It's just a particular quantum theory. It has a UN gauge group, right? But importantly, it has a gravitational dual with this particular background geometry, right? This ADS5 times S5. Now, the crucial point here for us is that in this gravitational theory, there are many interesting states, including these so-called giant gravitons, and as well as these interesting things, these new geometries, okay? Now, for these particular states, when the energy of these states, when it scales, and I'm also interested just in a particular sector of this quantum theory, okay? So when the energy of these particular states, when it scales like order n, so n here is the rank of the gauge group, they're dual to giant gravitons, and when they scale like order n squared, they're dual to these new geometries. And this theory was laid out quite nicely in this very well-known paper by Majorization and collaborators. Now, the operators that are living in the quantum theory, right, in the conformal field theory, that are dual to these states, they have been built, so they're known, and they're organized by irreducible representations of the UN. Okay, so just to give you a quick example of how one can build these kinds of operators, you can think about building operators with 3 Z fields. So Z is a matrix, it's a particular scalar field that lives in the quantum theory. If we have 3 of them, we can do the following. We need to take traces to make them gauge invariant. But if there's 3 Z fields, we can take the following. We can have trace Z cubed. We can have trace Z times trace Z squared times trace Z, and then trace Z cubed. Okay. Now what's quite interesting. So if you're trying to build a gauge invariant operator of n Z fields, then the particular trace that you get corresponds to a permutation of the symmetric group, right? So Sn, that's the symmetric group. It's the group of permutations of n elements, basically. Okay. So each multi-trace corresponds to a permutation. And then to actually build the operator, you take linear combinations of these particular traces, and the coefficients of this linear combination are the characters of the permutation inside this irreducible representation of the UN. Okay, so these are the sort of the famous Schur polynomials. They're gauge invariant operators. They diagonalize the inner product exactly in the free field theory limit.
Can you say more about the character of these operators? Hermitian or unitary or something?
Basically here I just mean, so I construct the element that corresponds to the permutation, that's a particular matrix, that corresponds to that irrep of the UN, and then I just take the trace. So yeah, basically, so I've got a particular irrep, I figure out what the matrix is corresponding to the permutation, and then I take the trace. That's what I mean by the character. Okay, good. So another interesting or another important element or important ingredient for the story are the Casimir operators. So we can build Casimir operators by taking products of these E matrices. So these E matrices are basis matrices for the UN. And so if I want to build sort of these higher Casimir operators, CK, I take a product of K of these E matrices, and then I also summing over repeated indices. And these Casimirs live in the center of the so-called universal enveloping algebra. Okay? And it is known that if you have complete knowledge of all n Casimir operators in the UN, it allows you to uniquely identify the irreducible representation, right? It allows you to uniquely identify the irrec or the state R. So, you know, if you, for example, have your Casimir operators and you maybe act on some operators, if you know all of the eigenvalues, you have enough information to label the states. And there's sort of a standard reference for that. Now, an interesting question that you might ask is, what do these Casimir operators correspond to in the dual theory? So all of this was happening in the gauge theory, in the quantum theory. This gauge theory has a gravitational dual. So what do these Casimir operators correspond to in the gravity theory? So it turns out that they correspond to these to multiple moments in the gravitational solutions. So just roughly speaking, if you write down the metric in the gravity theory, the fields in the metric, you can perform a multiple moment expansion in them. And then the Casimir operators are encoded into the multiple moments. And then this is kind of outlined in detail in this bottom reference over here by Balasubramanian and also collaborators.
So there are exactly n multiple movements?
Yeah, I would. I'm not sure if there's exactly n. So at the very least, I know there are order n of them. But yeah, so I mean, for that, I think I need to check in a little bit more detail. But certainly for the next statement, an observer in the gravity theory needs to measure all n multiple moments, or at the very least, they need to measure order n multiple moments in these solutions to have enough information to reconstruct the state. So again, this is also explained in this particular reference over here. However, right now the catch is in the semi-classical limit. So for an observer in the semi-classical theory, they can only measure up to can only measure these multiple moments up to the Planck scale, right? Which in this theory goes like n to the 1/4. So basically, the take-home message is that in order for an observer to perform enough measurements to have enough information to identify the state, right? The irreducible representation, they need to measure order n of them, right? Order n moments. However, in the semi-classical limit, they can only measure order n to the 1/4, right? Sort of best case scenario. So in principle, information is necessarily lost about the state, right? Such an observer can no longer uniquely identify the state that they're looking for. Okay. Now, it turns out that we can transform this problem into a problem in the representation theory of the symmetric group. Okay. Now you can show, right? So if you take one of these Casimir operators, these higher Casimirs, and you act with it on these multi-traces, you can write this thing over here on the right-hand side of the equation. So this operator over here in the subscript, that is an operator and it's acting in the center of the symmetric group algebra. Okay, so you can sort of, you can show that, and that was outlined in this nice paper by Kimura and Ramgulam. So, okay, so that's good. Now, these CKs, these sort of corresponding Casimir operators, can be written or are given in terms of something which we'll call in this talk central cycle operators. And we'll write them as T2, T3, and all the way up to TK, right? So these CKs can be written in terms of these T's, right? So what do I mean by these T operators? I just mean that they are sums of permutations. So for T2, for example, it's the sum of all 2 cycles, right? Or transpositions. For T3, it's the sum of all the 3 cycles, and same thing for T4, and so on and so on. And these elements over here, these operators, they live in the center of the symmetric group algebra. Now, importantly, if I consider the T2 all the way up to Tn, so if I'm thinking about the symmetric group Sn, and I focus on T2 up to Tn, it's been shown that those cycle operators, the central cycle operators, they generate the center of the algebra. Okay? And that was shown in a paper with myself and with Sanjay some time ago. Okay, so good. Now that fact is related to another fact, and this fact is the following: the normalized characters. So the characters again, the set of all the normalized characters of T2 up to Tn, okay, is distinct over the irreps R, right? So R here now is an irrep of the symmetric group. So basically, this list of elements or this list of values, T2 up to Tn, is distinct over the irreps. So if I change the irrep R over here and I let it run over all irreps, each list of values is distinct, is unique to each R, basically. Okay, now even more interesting, right? So it turns out that you don't need T2 all the way up to Tn. You only need, for example, T2 up to Tk, where k is smaller than n. So typically speaking, this subset will suffice to generate the center. Now this happens, again, if and only if the corresponding list of normalized characters, again, is unique over the list of the irreps. Okay. And by normalized here, so same thing, I construct the matrix inside this irrep R corresponding to this summation of permutations, right? I take the trace of that, and then to normalize it, I divide by the dimension of the irreducible representation. Okay, but importantly, if this list is unique over the irreps R, then it succeeds in generating the entire center of the algebra. Okay, so in this case, distinguishing between the irreps is possible, right? Because I can just use this list of elements, right? If this list of elements is unique for each R, I have enough information to distinguish between the irreps. Okay, good. So now typically what happens, so if we increase n but keep k fixed, so if the size of our symmetric group increases, but we still consider T2 up to Tk, for example, then typically degeneracies in the list of normalized characters will start to appear. Okay, so in that case, not all of the irreps will be distinguishable. Okay, so then what we do, we then go to the next highest cycle operator, so Tk plus 1, we include that in the list, right? And then we study this corresponding list of normalized characters. And then we hope then by including Tk plus 1, that will break the degeneracy. I'll show an example in a moment. Okay? So crucially, we define this all-important integer, k star of n, and for us, that is the minimum number of Tk operators needed to distinguish between all of the Young diagrams at a fixed n. Okay, so at a fixed energy or fixed number of boxes. So let's have a look at a quick example. Okay, so if we start with T2 and we study the normalized characters of T2 inside some irrep R, now it turns out that there are no repetitions at all in that value for small values of n, right? Small values of the symmetric group. So it turns out for n equal to 1, 2, 3, 4, and 5. There's no repetitions or no degeneracies in the normalized character of T2. So we can say that T2 generates the center. However, for n equal to 6, there appear degeneracies for the first time. So at n equal to 6, so if you think of Young diagrams of 6 boxes, there are 11 diagrams that you can construct. And you can see here, 2 of them are degenerate. And over there, 2 of them are degenerate. Okay, so again, this is the list of values for the normalized character of T2. So the diagrams or the partitions that correspond to that normalized character, it's these 2. Okay, it's those 2 representations basically. So, you know, we cannot distinguish between this state and that state, right? We cannot distinguish between these 2 states just by studying the normalized character of T2, right? Because there's a degeneracy there. So what we do, we include now T3, right, the next highest cycle operator, and we study this new list, right? We study this new list, and then this is the corresponding, I don't know if I can try and
sorry, no, you need to be on the screen.
Oh, I see.
Okay, just click on it.
Oh, great. Yeah. Okay, thank you. Yeah, it's much better. Okay, great. So if we study the list of T23, here are the list of normalized characters. Where was the original degeneracy? It was over there, right? But now we can see by including T3, the degeneracy is broken, right? So now we are able to distinguish between those two. Okay, so anyway, so information loss was studied and quantified to a certain extent when a restricted set of Casimir operators was known, and with the states having a fixed energy n, or fixed numbers of Young diagram, or fixed numbers of boxes in the Young diagram. So again, that was done in the paper with myself and Sanjay. So we computed entropies and codimensions and stuff like that. However, so I say here, the task of distinguishing between the Young diagrams with a restricted number of cycle operators, T2 up to Tk, it raises some, at least for me, it raises some interesting questions. So for example, what are the properties of the Young diagrams whose normalized characters are degenerate? So just, for example, what is it about these two diagrams specifically that they should have the same normalized character value for T2, right? So this is the sort of question that motivated this work. So in so doing, I will posit a conjecture that allows me to establish an upper bound on K star of n. Okay. So good. So in order to get to this conjecture, I have to explain a little bit of, well, it involves something called majorization or the dominance ordering. So majorization, so if I've got two Young diagrams, let's say X and Y, we say Y majorizes X, okay, and it's written in this particular way, if the corresponding row sums of the Y diagram is always bigger than or equal to the corresponding row sums of the X diagram. Okay, so maybe this is better explained in an example. Okay, so let's see how we go with this. So here we've got two Young diagrams. Okay, so 4, 2, 0 and 3, 2, 1. Let's see which one dominates which one. So what we do, we first look at the first entry. So we've got 4 and 3. So we say, okay, that's great. 4 is bigger than 3. Okay, so this diagram starts off dominating the 3, 2, 1. Okay, good. So then we add the next element. So we say 4 plus 2, that gives us the 6. And then 3 plus 2, that gives us 5. So 6 is still greater than 5, so that's good. And then when we add the last one, 4 plus 2 plus 0, that gives us 6. And 3 plus 2 plus 1, that also gives us 6. This last equality here, that's non-negotiable. You must always have an equality when you add the last entry, because these are Young diagrams with the same number of boxes. Okay? So basically, from these row sum relations, okay, on the left here, we can say that 4, 2, 0 majorizes or dominates 3, 2, 1. Okay, so that's good. Yeah, let's have a look at another example. So these two, 4, 1, 1 and 3, 3, 0. So first thing we do, we look at the first entry. So 4 is greater than 3. Okay. However, when we add the second entry, so we do 4 plus 1, that gives us 5, and 3 plus 3, that gives us 6. So now the inequality sign has swapped directions. It's now facing towards the other Young diagram. And of course, when we add the last element, 4 plus 1 plus 1, that gives us 6. And 3 plus 3 plus 0, again, that gives us 6. So according to this particular scheme, these two diagrams are what's called incomparable, right? So now this, and it's known that this majorization relations or this dominance ordering, it establishes a partial ordering on the space of Young diagrams. Okay? And if you remember, it is precisely these two partitions, right? These two diagrams that had degenerate values for T2, right? 4, 1, 1 and 3, 3. Okay. So, okay, one more example. It's just to illustrate a particular point. So if we think of these complicated looking things here, they're both diagrams of 28 boxes, right? Or partitions of 28. if we construct the row sums, or if we study the row sum relations, okay, we can count the number of swaps. So of course, we look at the first entry, 8 is bigger than 7. Then you do 8 plus 6, that's 14. 7 plus 7, that's 14. So that's fine, that's allowed. But then we've got over here, 1 swap, 2 swap, and we've got 3 swap. Okay, so how many, in total, how many swaps of the direction of the inequality sign occurs? It's 3. Okay, and then for later on, just to summarize these row sum relations, okay, instead of writing this out in a long, complicated way, I will just use that notation just to summarize the row sum relations, okay, just to make the notation a little bit easier. So we define this integer k swap between 2 diagrams x and y, right? So it just literally counts the number of swaps of the inequality sign. And for me, I'm interpreting this integer as a measure of how incomparable x and y are, right? And it's based on the number of swaps. Another integer, there is a finite number of integers which I define in this talk, so just bear with me. So let the integer k star of y1 and y2, for 2 diagrams y1 and y2, let that be the minimum number of t's, right, tks, for which t2 up to k star, right, t2 up to tk star, those corresponding normalized characters can distinguish y1 and y2. Okay. Now, if we have some level of degeneracy, so let's say this list of normalized characters, right, this list of values for y1 and y2 is the same, okay, and it goes from t2 up to, I don't know, tk dash, right? However, if we include one more cycle operator in exactly the same way as we've done before, if that breaks the degeneracy, then what can we say about this k star? Okay, what can we say about that k star? We can say k star of y1 plus y1, y2 is this k dash plus 1. Okay, so that's what we've got. Now we go to this conjecture, right? So if we have a certain level of degeneracy in the Young diagram pair, y1 and y2, that goes from t2 up to some integer, tk dash. Okay, so if this list of normalized characters is the same for this pair, then we have this inequality that must be obeyed. Okay, so now this is my conjecture. So on the left-hand side, we've got the level of degeneracy, k dash, and that must be less than or equal to k swap plus 1, right? So what I'm saying here is that the level of degeneracy of the normalized characters is bounded by how incomparable the 2 states, 2 diagrams are. Okay, so that's my conjecture. So, just for example, if k dash is 2, right? So if only T2 is degenerate, in order to satisfy this inequality, K swap must at least be 1, right? So that's, the minimum K swap must be 1. And if K dash is 3, right? In order to satisfy this inequality, K swap must be 2, and so on and so on, must at least be 2. Okay, and as a corollary to this, if I put this equation 3, or this inequality, together with this equation for k star, right, we can say that k star, right, the minimum number of t's needed to distinguish just y1 and y2 is bounded again by how incomparable the 2 partitions are, right? But we've got this plus 2 now. So just very quickly, what does this mean? So let's go back to those 2 awful Young diagrams that we saw just now. We measured k swap for these 2 states, that was 3. So using my conjecture, we can see that the level of degeneracy is bounded by 4, cannot be higher than 4, and k star for this pair is bounded by 5. Okay, so the upshot of this is that if we take the normalized characters of T2 up to T5, it's guaranteed to distinguish these 2 particular states. We might not need all of them, so maybe, maybe we just need T2 and T3, right? But this list of operators is guaranteed to distinguish them. And just quickly, we can establish, using the story, we can establish an upper bound on K star of n. So if I think that K swap max, okay, now that is the maximum number of swaps between any pair of Young diagrams with n boxes, Okay, so, I mean, again, maybe I explain this through an example. So again, if we think of partitions of 28, so Young diagrams with 28 boxes, there are just over 3,700 Young diagrams. Okay, now suppose we know that the K-swap max is equal to 4. So that's the maximum number of swaps that any pair of Young diagrams have in their row sum relations with that number of boxes. Okay, so there exists pairs for which K-swap is equal to 4, right? K-swap is equal to the maximum. So from the conjecture, right, and corollary, we can say that K star is equal to 6, right? For these particular pairs. So we conclude that T2 up to T6 is guaranteed to distinguish these pairs, right? However, also T2 up to T6 is guaranteed to distinguish all other pairs because all other pairs will have a fewer number of swaps, right? Remember, K-swap max or 4 was the maximum, right? All other pairs will have fewer number of swaps and therefore will be distinguished using a fewer number of T operators. Okay, so the upshot of this is that I now have an upper bound for my K star of M. Okay, it's equal to the maximum degree of incomparability between states, of course, plus that integer there. Okay, so this is the crazy conjecture, right? So let me try and outline briefly some evidence behind this conjecture or supporting this conjecture. So just to give a flavor of the data that I collected. So again, if we consider a pair of if we consider Young diagrams having a level of degeneracy or KDH, okay, so all Young diagrams having this list of degenerate normalized characters, right, T2 up to TKDH. If I collect all of those Young diagrams and I put them in subsets, okay, so for example, you know, Y1 and Y2, they have the same values for that list over there. And these three diagrams over here, those three states, Y3, Y4, Y5, they have all the same values for this list over here. And then, yeah, same for Y6 and Y7. Okay, so then what I do, I pair in each subset, I pair all the diagrams in all possible ways, and I measure K-swap for each one of them. So, you know, for example, for this subset, there's only one way I can pair them, right? So I get a K-swap for Y1 and Y2. For this subset, I pair, you know, 3 with 4, 3 with 5, and 4 with 5. I measure K-swap for each of them. And then the last thing for that subset. Okay, so, you know, again, for some level of degeneracy, I measure that K-swap. So just say for argument's sake, ignoring the conjecture for now, let's say that K-swap for the first pair was 2, and K-swap for the other subsets was 1, 0, and 2, and the K-swap for the last pair was 1. Then we just tally up these numbers, and then we say that, you know, according to what we found, there's one pair of diagrams with 0 swaps. That was Y3 and Y5. Okay. Then we have 2 pairs with 1 swap. That's this one and that one. And then we have 2 pairs with 2 swaps. Okay, so that's, you know, just to give a flavor of the data that I generated. So let's have a look at Young diagrams with degenerate T2. Okay, that's cycle operator T2. So I started off at n equal to 6. So Young diagrams with 6 boxes. Okay, we saw in the example that I showed that there were 2 pairs having degenerate T2 value. You can measure K-swap for each one of them, and K-swap is 1, right? For each pair, so there's 2 pairs, K-swap is 1. Okay, and then I generated data for n equal to 6, n equal to 7, all the way up to n equal to 27, right? Now, what's crucial, the crucial point of this table is that I detect 0 Young diagram pairs with 0 swaps. Okay, so 1 again is the minimum number of swaps that I need. So this is in line with my conjecture. Okay, I also generated data for Young diagram pairs having degenerate T2 and T3 values, right? So this is the corresponding table that I've generated. The important thing here is I detect 0 Young diagram pairs having less than 2 swaps. Okay? Again, in line with that inequality that I wrote down, in line with my conjecture. Young diagram pairs with degenerate T2, T3, and T4. Okay, so again, this is in line with the conjecture. The important thing here is I detect 0 young diagram pairs having less than 3 swaps.
Okay, can I ask us to?
Yes, not at all. Yes.
Your data.
Yes.
When the swap starting getting non-zero.
Yes, exactly.
I would have expected naively that the numbers increase monotonically, but they
I
don't.
was just thinking the same thing.
Yeah, meaning the numbers in these columns.
Yes, yes. I would have imagined, 1, 2, 3, 4, but it's 4, 3.
As soon as they get
Yeah.
large, as soon as they get large, they will.
It's okay.
Exactly, exactly.
Is there a reason for that or not?
Not a good reason that I think that's a very good question actually. In the previous paper with myself and Sanjay, we tried to study, we plotted graphs of entropies and sort of the degeneracy number and stuff like that. And for some of these things, we were getting sort of linear relationships for the codimension and sort of very smooth looking curves for entropy and stuff like that. But basically, in short, I don't have a good understanding of why these integers increase.
That means it look linear.
Exactly, right? So, I mean, that's a good question, right?
Are these exact results?
Yes. Yes. Precisely. So, really, all I've done in Mathematica is I'm able to calculate the normalized character amongst the irreps. Then, for a given degeneracy, I ask Mathematica to pair them in all possible ways. Again, I ask Mathematica just to count the number of swaps, and then I just basically document it on this table here. Okay, so this pattern does. I just show 1 or 2 more tables. So again, for the next level of degeneracy, T2 up to T5, the pattern continues, right? I detect 0 young diagram pairs having less than 4 swaps. Okay, and then at this point at n equal to 65, my little MacBook was working very hard. Okay, so this was the data that I managed to generate. There's one more interesting thing that I can show. For kth equal to 6, right? So in other words, the first time partitions appear for which T2 up to T6 are degenerate occurs for n equal to 80. Okay, so now there are a staggering number of partitions, a real immense number of young diagrams with 80 boxes. However, there are 3 pairs. Okay, again, just very bluntly and brute force kind of method done in Mathematica. There are 3 pairs of diagrams that have this degeneracy. Here's one of them. Okay, so let's just look at one of these pairs. Let's look at the row sum relations. Okay, so first of all, 16 starts off, 16 is bigger than 15. So that's the reason for that first inequality sign there. However, you then do the row sum relations. So here we find 1 swap, then 2 swap, right? It hasn't swapped back again, so that's 2 swaps. Here we've got 3 swaps, 4 swaps, and 5 swaps. Okay, so again, the pattern continues, right? So now the first time partitions appear with that level of degeneracy, we've got 5 swaps in the row sum relations. Okay, so that's kind of summarized on this table over here. So that's good. Again, for a certain level of degeneracy, you need a minimum number of swaps. Okay, so that was just kind of numerical or computational or some experimental data. Okay, so do I have anything analytic? Can I, provide even maybe a little bit more evidence for this? Okay, so I can, just to a certain extent. And what's important for this small little subsection of the talk is the shifted young diagrams. So if I pick up the young diagram with Y1 boxes in the first row, Y2 boxes in the second row, and so on and so on, I form the shifted, the corresponding shifted quantity. So each row is shifted by an integer. Okay, so that's important. Now you can show that for a partition pair, Y and Y prime, so for those 2 young diagrams, the normalized characters for T2 up to TK, they're degenerate if and only if the corresponding power sums in the shifted row lengths are also degenerate. Okay, so what's happening here on the left side? This is the power sum. Okay, so Q is some exponent. we've got the power sum of the Young diagram, or the shifted Young diagram Y, and on the right-hand side, we've got the power sum of the shifted Young diagram Y prime. Okay, and if we've got T2 up to Tk, this exponent here, right, giving us the power sum must be 2 up to K. Okay, so you can show that, right? So sort of if and only if statement. Okay, so for me, I take the difference, right? So basically, I take this, all these bunch of terms over to the other side, and I study this delta object here, right? So I look at the difference between those shifted row sums. Okay, so let's just check that things are working as they should. So here's our nice, interesting pair of diagrams of empty boxes. Now, I claimed that in my data, I found that T2 up to T6 was degenerate. Calculating the power sums, okay, so if everything is working as it should, and these are the results of my calculation, I found that delta 2, delta 3, all the way up to delta 6, those are all equal to 0, right? And then delta 7 is necessary. Well, it's not 0, right? It's bigger than 0. Okay, so instead of studying the normalized characters, I'm studying these now, power sums in the shifted Young diagrams. Okay, so just some analytic arguments. Let's just check. Okay, 20 minutes. So it's known, right, for K swap equal to 0. Okay, it's already known that the normalized character for T2 they cannot be degenerate. Okay, so that was given. There's a nice proof of that in this sort of monograph, sort of monolithic textbook. All right, so that's good. So according to my construction, I should have delta 2 not 0 or not degenerate. Okay, so delta 2 should be positive, and by something called the Karamata theorem, one can indeed show that that's true. Okay, so there's a reference, that was at least useful to me for the Karamata theorem. I can always discuss that maybe after the talk, right? So in interest of time, I didn't explain what that was, but you can show that delta 2 is positive. So the conclusion that I draw from this, okay, is that if delta 2 is to be equal to 0, I cannot have K swap equal to 0, right? I must have at least K swap equal to 1, right? Because if K swap is 0, I necessarily have that. Okay, so let's now think about the case where K swap is 1, right? So we just start off with 0 swaps. Now we look at the 1 swap case, and so on and so on. So K swap equal to 1, I assume K swap is 1. I also assume that delta 2 is 0, okay, because I can now, because I've had at least 1 swap. So schematically, this is what my diagrams look like. I've labeled the row in which the swap happens by S. Okay. Oh, sorry, this one here on the right-hand side should say YF. Okay, so for the final Young diagram, the one on the left should say YI. Sorry about that. Now, in order to get from the left diagram to the right diagram, okay, I can imagine a series of 1-box moves. So in this construction, everything below this red dashed line, I can move 1 box, 1 box, 1 box, perform a series of 1-box moves, so that there's a net movement of boxes downward. Okay, so if I pick a box, it can move downwards, and everything above this red dashed line, there's a net movement of boxes upward. Okay, so that the diagram on the right in the top region dominates the diagram on the left. The diagram on the left in the bottom region dominates the diagram on the right. So that's my, K swap is equal to 1. If I assume that delta 2 is equal to 0, okay, I can show just by using those rows, the power sums, I can show that delta 3 is necessarily positive. Okay, so happy to discuss the details of the calculation, but yeah, in time, they're not. So the conclusion that I draw from this is that if delta 2 is to be 0 and delta 3 is to be 0, I cannot have K swap equal to 1. Right? So I must have 1 higher swap, basically. When I get to 2 swaps, that's when this construction of mine breaks down, and then I basically have no idea what else to do. Okay, so for 2 swaps, I was only able to to study a very simple case, right? So a case where, so again, this is a schematic Young diagram. These dashed lines indicate where the swap happens. And here I imagine, so my construction is, I imagine that I perform one movement of a single box, right? So one box move in the top region, right? So somewhere to a higher row. There's one downward box movement in the middle region, and there's one upward box movement in the bottom region. So that gives me a very simple case where I've got two swaps, okay? So that's good. I further assume that delta 2 and delta 3 is 0. I can do that because I've got two swaps now. And just in this very simple case, I'm able to show that delta 4 is necessarily positive. So the conclusion, again, that I draw from this is that in order for delta 2 to be 0, delta 3 to be 0, and delta 4 to be 0, I cannot have two swaps. I need to go to a higher swap. I need to go to the next one. Okay, so that's where my analytic evidence kind of stops. In the last 15 minutes, I discuss, if you were thinking that there's not enough conjectures in this talk, I've got one more. But it's kind of interesting, all right? So let's play around with this. So we note the following. The first time that Young diagram pairs with one swap appears is for n equal to 6. So Young diagrams are 6 boxes. Okay, so good. The first time that Young diagram pairs having k swap equal to 2 appears is for n equal to 11. So 11 boxes. Okay, so now an interesting question. Okay, is what is the smallest n for which Young diagram pairs appear having a certain number of swaps, right? Having L swaps, right? And I will call this n min of L. Okay. This is interesting because, if we go back to that integer k swap max, which was an upper bound for my k star of n, right? K swap max is equal to L, some number of swaps, for some range of n values, right? Typically from n min up to n max. Okay, so, for example, for the range n equal to 6 to n equal to 10, k swap max is 1, for example, right? So, okay. So how do I solve this problem? Or what light can I shed to this problem? I'm not telling this is a solution. This is just a crazy thing that I have found. Okay, so I propose an algorithm for constructing Young diagram pairs with the least number of boxes, right? So the fewest number of boxes, but they have L swaps. So here's what I found. I start with y equal to 0, okay? And y prime, the other Young diagram, I set equal to 1. So here I'm arranging the Young diagrams in ascending order, okay? So then what I do next is I add the smallest integers possible to y and y prime so as to either produce a swap in the row sum relations or an equal sign in the row sum relations. However, one more constraint, with each addition, I have to maintain a valid Young diagram. Okay. Now, so with that in mind, it seems to be, at least what I found in playing around with this, that the optimal row sum relations seems to be given by that. Okay, now I'll discuss an example in a moment. Okay, but a nice thing to note initially is that we seem to alternate between equals, swap, equals, swap, equals, swap. Okay. So you ask, potentially you can ask yourself, how many equal signs do I need? Okay. At some point, right? Because at some point, the equal signs, we don't have equal signs anymore, and we just have swaps over there until finally we have the sort of the last equal sign. Okay. So it turns out that for an even number of swaps, if L is even, how many equal signs here do we need? L divided by 2. If L is odd, we can have two possibilities. We take the floor, right, or the lower limit of L divided by 2, or we can also take the ceiling, the upper limit of L divided by 2. Okay, so let's have a look at an example. So if I consider the case with 5 swaps, L equal to 5. L is odd, so I can have 2 pairs. I can have one pair with 3 equal signs in the row sum relations, or I can have another pair with 2 equal signs in the row sum relations. Okay, now, yeah, okay, so the row sum relations, right, look like the following, right? So you can see for each pair, there are 5 swaps. The top pair has 3 equal signs, beginning with the bottom pair has 2 equal signs. Okay. So actually constructing these partitions, that's what I get. Okay, so for y1 and y1 prime, okay, those are 2 Young diagrams that have those row sum relations, and for this bottom pair, it has this bottom row relations over there. Okay. Now what I do, so how do I get the n min, right? So how many boxes are these Young diagrams, or how many boxes do these Young diagrams have? I just add them up, right? Add up the entries, and I get 36. So my claim is, based on this crazy construction, is that the first time that Young diagrams appear with 5 swaps is for 36. Okay. So using this this weird construction, okay, I generate this table of integers. Okay, so you know, using this construction, I pushed this even, you know, up to 12, and it turns out, you know, the claim is that the first time that Young diagram pairs appear, having 12 swaps is at 146. So okay, so that's the conjecture. Is there some evidence that I can offer in support of this? So the first thing that I did was I again took Mathematica. For a given n, I can generate all possible Young diagrams in Mathematica, and then just what I did, I paired them in all possible ways, and I measured k-swap for all of them. Just by doing that, I was able to verify the table up to 5 swaps. So all these values here I checked explicitly using Mathematica. So I mean, you know, I wish I could find maybe a better way to code this, and it was just very much brute force method. But I managed to analyze it up to there. Also very interesting, okay, so if we have a look at this list of integers, the 6, 11, 18, so on and so on. So if you punch this, so thanks to a suggestion last week from someone at UCT, if you just punch this list of integers into this online encyclopedia for integer sequences, it turns out that this is actually known, right? So someone has actually come across this sequence of integers. The reference, I mean, the entry number is that basically, okay? And it turns out that there's actually a number of that series. Maybe. So that means quite 100,000. Quite, yeah. So it turns out that on this web page, it's given a closed formula for these integers, and there's even a generating function for this sequence. So yeah, so you expand this guy, and the coefficients of this expansion reproduces all of this. Okay, so what I wasn't able to obtain from this web page yet is, you know, what was the problem that the person was studying that led to discovering this integers or this sequence? Yeah, not sure how they discovered what problem they were trying to look at, but anyway, there it is. Now, interestingly, if I take my construction, right, and I just consider the case that L is even, but also L over 2 is even, okay, so if I just look at that particular case, you can write something very nice for this Young diagram construction, okay? And if I add up all of these entries over here, it gives me a very nice formula, okay? So 3/4 L squared plus 3L plus 2, okay? Now, what I have been able to show is that this formula given on the online encyclopedia is exactly the same as the formula that I have found over here, but I need to take the ceiling, right? So sort of round it up. For even values, for even swaps, they're identical. For odd swaps, I need to take the ceiling basically. Okay, but I'm still investigating this at the moment, right? It's very strange. Then the last thing that I've done, so I was looking at asymptotics. Okay, so it's very interesting. So you know, when n becomes very, very large, what can I maybe say about some things? Okay, so of course when so, you know, I have this relation over here. This k-swap max is equal to L, and that's that's true for some range of n values. Okay, so n min up to n max. So if I add an extra one, so n max plus one, I typically then generate diagram pairs with L plus one swaps, right? Then I generate an extra swap there. If I, if I do n max plus one. So in the case of very large L, right? So if I take both n to be large and L to be large, it stands to reason that as the number of boxes in the Young diagram becomes very, very, very large, also the number of swaps becomes large. Okay, I can make these following approximations. Okay, so basically, the conclusion I draw from this is that all of the n values in this range at large L behaves like this 3/4 of L squared. So there's a nice sort of L squared relationship. Then what I did, if I invert, right, this relationship here to find L, right? So if I invert this to find something for L, goes like a square root of n, right? I arrive at this behavior for K-swap max. So K-swap max basically behaves like a square root of n, and that's true for all n values, or at least my conclusion is it's true for all n values for which the maximum number of swaps in the Young diagram row sums is approximately equal to L. Okay, and you can also push this a little bit. There's some wiggle room as well. So why is that important? So if you remember my conjecture, K star of n, which was this all-important integer, the minimum number of t's needed to distinguish between the states, that was bounded by K swap max, and now I've got some sort of dependency on n for K swap max. Okay, so this table over here, comparing some K star n values that are known that we've actually computed, comparing that with this upper bound here. It's all behaving very, very nicely, that sort of thing. Not a huge amount of critical information here. So yeah, maybe I just conclude now. So what have I tried to speak about? So now this dominance ordering on the space of partitions or Young diagrams, it seems to have offered some insight into the problem of distinguishing the irreducible representations of the symmetric. Okay. For this, if you remember, I introduced this incomparability measure, this counting of the number of swaps, and that basically led to this nice sort of conjecture that I put forward. I found computational data in support of this conjecture, small amount of analytic evidence as well for the conjecture. Okay. And remember, this was the conjecture, it was a necessary condition for the irreps of R, or the SN, to have degenerate normalized characters. Then that led to an upper bound for K star of n. Remember, so this was the number of t's needed to distinguish between the irreps. Now, working backwards, right, so going back to the gauge theory, the quantum theory, this was the number of Casimir operators needed to distinguish between the states in the gauge theory. And then going to, using ADS CFT, this was telling us about the number of multiple moments that an observer in the gravity theory needed to measure in the ADS, right, to distinguish between those very heavy states, those almost like those black hole-like states in the gravity. Anyway, so that's all I have for the moment. More interesting questions to look at in the future. But yeah, with this, let me say thank you for your attention. Thank you very much.
Yeah, thank you very much.